Welcome to Module 2, Finite Automata, Video 2. In this video, we're going to talk about non-deterministic finite acceptors, or NFAs for short. We'll go over the formal definition, some examples, and the concept of closure. All right, so let's talk about an NFA. Let's start with the formal definition of an NFA. The formal definition is the same as a DFA. It is a 5-tuple. Q is the finite set of internal states. In other words, it has a finite set of states. It has a finite set of symbols called the input alphabet. The transition function for an NFA is very different than the transition function for a DFA because it allows lambda transitions, and it'll be best demonstrated by when I show you a demonstration, but also you might not just end up in one state. So it's not just one symbol from one to the next state. You can have lambda transitions, which are jumps, which may change, and you might end up with symbols in more than one state. You have the initial state, and you have the set of final states. And just like a DFA, if after consuming each symbol, if you end up in a final or accepting state, then that is language is accepted. That string is accepted as part of the language. All right, so there is in an NFA, there's also the extended transition function, where the second argument to the transition function, instead of being just a single symbol, it could be a whole string. And I'm about to show you an example that includes the extended transition function and also how a lambda jump works. So there are 3 differences between a DFA and the NFA. The first one is the range of the transition function. So the range is a subset of Q and not a single element of Q. So what does that mean? It means that you could read in a string, and as you're reading in the symbols, your range in a DFA, each symbol is going to go to one transition, to one state. But in an NFA, you could end up in more than one state in the range. So it's better to understand by a demonstration. Also, lambda transitions are allowed. A lambda transition is basically a jump. So you would make a transition without consuming an input symbol at all. That would be a jump. And in a DFA, you have to define every transition between every state for every symbol. And in an NFA, you don't always have to define every single situation, especially the ones that are not necessary. So let's take an example of the extended transition function. So if you take a look at this, we also have a jump here. So here we have a lambda transition. That means that you could be in state Q and Q0 and just make a jump without consuming any symbols over to Q2. That's what this a lambda transition is. So you could go here. Also, you could go 1, 0, then jump over here. Or with a 1, 0, you could end up in Q0. So that's an example of the extended transition function. If you're in Q0, so you're in Q0 and your input is 1, 0, you start here at Q0, your input could be back to Q0, or your input could be 1, 0, and then you take the lambda jump over to Q2. So the range for this extended transition is Q0, Q2. In this situation, we have an extended transition function because this is not a single symbol, but if you're in Q0 with a 1, 0, 1, the only place you'll end up is Q1 because there is no lambda transition. So this language is the language of any number of 1 zeros. So if you go 1, 0, that's accepting. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So that's what this language is. But notice you could go 1, 0 and end up here in not accepting. With an NFA, you have to try all options to make sure that you do not end up in an accepting state. So even though you could go 1, 0 and end up in a not accepting state, there is the option to go 1, 0 and end up in the accepting state. So therefore, 1, 0 is a string in this language. All right, here's an NFA for the same language. Let's build it. The empty string is not part of the language. Then you get an A, you get a B, you get a B. So now we have A, B, B, and we are in a accepting. Then you get any number of A's and B's before your ABB. Notice we have a transition here for A and we have a transition here for A. But that's okay because this is an NFA. So you could do any number of A's and B's here, but then eventually you're going to get A, B, B, and you will end up in the accepting state. So these are the transitions from Q0 with an A. Q0 with an A, you're either going to go to Q1 or you're going to go back to Q0. Then Q1 with a B, you're going to go to Q2. Q2 with a B, you go to Q3, which is accepting. Q0 with a B, you're going to stay in Q0. Q1 with an A is the empty set. The reason, if you're in Q1 and you get an A, we don't have to worry about that because this is an NFA. You don't have to define every transition. So this is an example of an NFA that solves this problem, for this language. And this is a DFA for the same language. Again, the NFA for the same language. All right, so what could be an advantage of an NFA? Well, let's see. What if you have a machine where the number of zeros is, okay, so we have an alphabet, 0, 1, and the number of zeros is a multiple of 3. So what would you do with that? You would construct a DFA. So here's a DFA. We started our initial state, 0, 0, 0, 0. This is not in any kind of order. It just means that in our language, the number of zeros is a multiple of 3. So every time you get 3 zeros, whether you get ones in the middle, you end up in an accepting state. Okay, and now I want a machine where the total number of characters is even. Okay, same alphabet, total number of characters is even. We said you can construct a DFA for that. All right, so here, same alphabet, the total number of ones and zeros. It doesn't matter if they're ones or zeros, but it's even. So we have one DFA at the top where we have 3 zeros, and we have one DFA at the bottom where the total number of characters is even. All right, now I want a machine where all strings have the number of zeros is an even number of 3, or the sum of all the zeros and ones is even. Okay, so now I want a machine that is either one of these two things. So how am I going to handle that situation? How am I going to build? And you can build a DFA for this, and it would be pretty complicated. But what you can do instead is you can create an NFA for this. You can create an NFA, and then you would just have your initial state in the NFA and add 2 Lambda transitions to each of the 2 different DFAs. And now you have an NFA that accepts this new language where all the strings, which this is has a typo in it, but that's right, where all the strings have the number of zeros is an even multiple of 3, that's this one here, or the sum of all zeros and ones is even, that one here. So this is an advantage of using a DFA. You just take your 2 NFAs and add Lambda transitions. So any string that you would put in here, you could take the jump to either one of these 2 situations. All right, that being said, let's talk a little bit about the concept of closure. We will talk more about closure because we haven't even really talked in detail about regular languages, but regular languages, the definition right now of a regular language is a language in which you construct a DFA for it. Okay, so if you can construct a DFA, then it is a regular language. And you can do a proof to prove that a language is regular by constructing a DFA. You can also, regular languages, you can also say a language is regular if you can construct an NFA. So if you can construct a DFA or an NFA, you define a language, which we've been showing you what you do. And if you can construct a DFA or an NFA for that language, that means it is a regular language. If you remember the hierarchy of languages, that is what the hierarchy of languages says, that that's what we would use. The automaton for a regular language is a DFA or an NFA. So what is this concept of closed? All right, so the concept of closed means that if I perform any of these operations on a regular language, the resulting language is still going to be regular. I repeat, if I have two languages, L1 and L2, and L1 is regular and L2 is regular, and I union L1 with L2, then the result of that is also going to be regular. Same thing, if I have L1 is regular, L2 is regular, I take the intersection of L1 and L2, that one will be also regular. If I have L and I take the complement of L, if L is regular, the complement will be regular. If L is regular, the reverse will be regular. If I have L1 and L2 and I concatenate them together, L1 is regular, L2 is regular, and I concatenate them together, then that's also going to be regular. And regular languages are also closed under positive closure and star closure. That means union them with themselves n number of times, and positive closure is without the empty string. All right, so now let's just look at an example. Here we want to prove by construction that if L1 is regular and L2 is regular, then the union of L1 and L2 is also regular. So we can do a construction, a proof by construction to show that this is true. So let's get started. All right, so the first thing we're going to do is, oh, shoot. Okay, well, I can't go back, but that's okay. I'm going to construct a DFA. So this is a DFA for L1, and this is a DFA for L2. So I can construct a DFA, one DFA, and two DFA. And so I know that L1 is regular because I constructed a DFA for it. And I know that L2 is regular because I constructed a DFA for that one. The next thing I do is so when I constructed these, this was the initial state and this was the initial state. But now I don't use this initial state anymore. I'm going to create a new initial state. I create a new initial state. And from my new initial state, this is just what we just did before, how we had the other two languages. I just create Lambda transitions from the new initial state to the previous initial states of my other DFA. So I created a new initial state and I added Lambda transitions. So now, that being said, I now have a NFA